we're going to be talking about insulators, conductors, and most importantly, what happens when you put two conductors together, which is what we call a capacitor. So, what is a conductor? Well, you probably have heard of insulators already. Like when you were a little kid wearing gloves. Oh, shit, I don't know how to draw those. I'm bad at drawing hands, sorry. Your mom probably told you these will help insulate your hands. What does that mean? Well, first you have to talk about what is that glove actually doing. Well, it's wrapped around your hand so tightly that no air can actually escape. Now, what is that doing for you? Well, you probably know that your body is extremely hot. It's around 100 degrees Fahrenheit, which is very hot, especially when you see the weather forecast go, oh, wait, 98.6 degrees? Well, that's my perfect temperature. That's what my body operates at. And then you go outside and you die in the heat. So, here's the problem. Your body's heat is constantly escaping from you and dissipating into the surrounding air. But what a glove does is it traps that air. It stops it from leaking out. It holds the heat that is being generated by your body and captures it. So the second after you put on the glove, I mean, you're not going to feel that hot, but as soon as you start putting it on, it's going to get warmer and warmer in here until it reaches hot enough for you to feel comfortable. So that's what a glove does. Now, how does I don't believe you. Ah, yeah, that was a lie, see? Okay. So, how does an electric insulator work? Well, that's a great question. Just the same way as a glove keeps in your body heat, an electric insulator is very good at keeping electric charge in. I don't know how to draw a sideways lightning bolt, sorry. It's very good at keeping electric charge inside it without letting it get out. And I mean, that's a good thing for a lot of reasons. Number one, without the existence of insulators, every single circuit would suddenly break down because there would be absolutely no way to stop the current from running at max speed. And eventually that would tire out the system and it would short circuit almost immediately. And second, insulators help us humans because, we're supposed to be the ones using these electrical systems and repairing them when they don't work right. When we touch something without an insulator, electric current is very dangerous, right? Because it really interferes with the way our body works. Our body has an electric current flowing all the way through it, through our nervous system. And controlled electrical shock throughout our body is the only way our brain can actually control it. So as soon as we get an electric shock from for example, an open circuit without using an insulator, then our nervous system basically immediately goes offline. It's short circuited, just like anything receiving too much power will. So insulators are very important. But now you're probably thinking, well, what happens if you go the other way? What if you had something very good at transferring electric charge? Well, that's what wires are made out of. That's why wires are metallic, because metal is a great conductor, both of heat and of electricity. Metal is great at transferring electric charge from one place to another, extremely great. Now, while that does mean it's good for transferring electric charge from one wire to another, it's also great for transferring electric charge from a wire to your hand and into your body, which is not as great. So that's what an insulator and a conductor does. But can we actually get into the math for a second? This seems very conceptual. So, how do they work when we're talking about electrostatics? Well, here's the thing. Conductors like these, are inherently not electrostatic. You can probably guess that because they're meant for moving around negative charge. If you're moving, you're no longer static. So, the first thing that you have to note is that any conductor is going to separate all positive charges on one side and all negative charges on the other. And as a result of that, because of the way Coulomb's law works, the electric fields of these two will cancel each other out. And there's going to be absolutely zero electric force inside this conductor. So nothing's going to get moved towards the negative side, nothing's going to get moved towards the positive side. Obviously, that doesn't hold outside the conductor, as out here, the electric fields no longer cancel, but actually become something much more difficult to handle. So, actually, they don't overlap this way. It would be something more like this, which cancels out to provide a horizontal effect. So, first thing to note, electric field inside a charge is zero, and hence the electric force is also going to be zero for anything passing through, which is good. Now, the second thing you want to note is that conductors by themselves are useful, but what happens if we stick two conductors together? That forms something known as a capacitor. Capacitors are very useful ways to transfer electric charge from one place to another, even better than just one conductor. Two conductors are better than one, is the general message. So, a capacitor, well, what does it do? It's storing positive electric charge in one end and negative electric charge at the other end. And of course, that means that the electric potential in one end is going to be significantly different from the electric potential in another end. You could almost even say there's a potential difference. And that's voltage. Now, some capacitors are more powerful and some are less powerful. More powerful capacitors can store more charge and thus rack up a potential difference that's very large very fast, while less powerful ones take a lot more charge to achieve the same potential difference. So, capacitance is defined as the amount of charge you need in order to, wrong way, is the amount of charge you need to achieve some amount of potential difference. A more powerful capacitor, since it can hold on to more charge, is going to create a potential difference quicker than a less powerful capacitor. So, the capacitance is just voltage over charge, the same way the electric field is the force over the charge. It's a proportionality constant, essentially. So, that's all about conductors, insulators, and capacitors. Thanks everyone for watching.